In some situations, the acceleration might be constant, like gravity, for example, or uniform acceleration problems that we will discuss later. If we take dt to the other side and integrate both sides, we'll get v minus v naught on this side and a times t minus t naught on the other side. Rearrange, and you will get this very famous equation that you've already seen in physics. An important point here, t naught is the starting time of your calculations. So think of it as the time you started your stopwatch. Usually, the problem starts from t naught equals 0, and that's why in most books you will see the equation written in this way. You can also write delta t instead of t. It doesn't matter how you write it, as long as you know that it means the time from start to finish. And make sure, please, that you always start writing your equations with your assumed positive direction. If we take this equation of v and place it in its definition and take dt to the other side, you can integrate both sides for s and t. And this results in this displacement equation. Finally, if we eliminate dt from both definitions of a and v, as we did before, we end up with a ds equals v dv. And by integrating both sides for v and s, we get our third equation, which is not a function of time. Let's look at a couple of simple examples. Initially, a car travels along a straight road with a speed of 35 meters per second. This is your v naught, and you can see that all three equations have v naught also. If the brakes are applied and the speed of the car is reduced to 10 meters per second in 5 seconds. So here you're given the final velocity v and time t. Determine the acceleration of the car. From what's given, the first equation is your clear choice to find the acceleration. Start by assuming the positive direction. The final velocity is 10, initial velocity is 35, and t is 5. The acceleration is -5, and that's because the brakes are applied, which means that the car decelerates or slowing down, and the acceleration points to the opposite direction. In this exercise, initially, if a car starts from rest, rest always have only one meaning, v naught equals 0, and increase its speed to 20 meters per second. This is the final v, in 50 meters, delta s or displacement. Determine the acceleration of the car. This problem has no time given and no time required. And with the given information, the third equation is our clear choice. By applying, you will find that a equals plus 4 meters per second square, which means the car is accelerating in our assumed direction. And that's because it increased its speed. Let's look at this one. A ball is thrown vertically up. Here, before you do anything, put this arrow of gravity pointing down, with initial velocity v naught. So just draw a particle showing v naught up. And he's asking, what's the maximum height reached? And we all know that at the maximum height, the particle stops before changing its direction, which means that v here is equal to 0. And delta s now is our maximum height. No time is mentioned in this problem at all, and with the given information of v, v naught, a, which is gravity, and the required delta s, our clear choice is the last equation. Applying the equation with the positive direction assumed up and taking v naught squared to the left side, we'll get this equation. Note that a is taken as -g because our assumed positive direction is up and the actual direction of acceleration is down. And here we end up with our solution for delta s, which is clearly positive because the negative signs on both sides cancel each other. This question can be asked in a different way, where the maximum height is given and initial velocity is required. In this case, you just solve for v naught from this equation instead of delta s. So just move 2g to the other side and take the square root of both sides to find v naught. Okay, here we have a ball thrown vertically upward, which means we have a gravity pointing down, as we said before, with a speed of 15 meters per second, which is initial v, or v naught. Determine the time of flight, which means we'll be using either the first or the second equation. When it returns to its original position. And this means if it starts and ends at the same position, delta s is simply equals to 0. And because the first equation has no s in it, the second equation is our clear choice to solve this problem. If positive is assumed upward and take s naught to the other side, s minus s naught is equal to 0. And you can also divide by t to further simplify the equation. Applying a equals minus 9.81, the time is found to be 3.06 seconds. If for any reason you get negative time in your problems, go back and check your positive direction assumed, and also check the direction of the vector variables, like for example s, v, or a. Another way of solving this problem is by taking advantage of the problem symmetry. Physically, if you throw a ball up with the speed v naught, it returns to you at the same height with the same velocity. It's the simple law of conservation of energy that we'll see later in the course. Therefore, when the particle returns to its original position, its velocity is equal to the initial, but in the opposite direction. If we have the initial and final velocities, and the acceleration also, we can find the time from the first equation. Assuming positive up, the final velocity v equals v naught, but in the opposite direction, which is negative. V naught positive up, and a is minus 9.81. The time is 3.06 seconds, just similar to what we found by the first method.